Dear students, welcome to lecture 17 on free radicals. So this topic on free radicals we will be taking in two parts. So let us start the first part. What are free radicals? Free radical is any atom or group or molecule that possesses one or more unpaired electrons. So therefore, if we apply this definition to atoms like hydrogen, halogen and alkali metals, we find that all of them have odd number of electrons and thus can be called as radicals. Hydrogen, chlorine, silver, sodium and even oxygen gas O2 is a diradical because these two electrons are not paired with each other, they are unpaired, and therefore this is known as a diradical. Now let us try to understand why free radicals are so important to us in chemistry and in other places. You may not realize, but free radicals are almost everywhere. Even in the air that you are breathing now contains oxygen, which we have just seen is a diradical. So other free radicals are also present inside our body, and they are superoxide, hydroxide radicals, hydrogen peroxide, and even transition metals like iron and copper. Some traces of them are present, which are free radicals. Cells continuously form and decompose free radicals using specialized enzymes about which you will study in biochemistry and other subjects. If these free radicals and their concentrations are not controlled, it can lead to serious damage to the DNA, protein and lipid and ultimately cause cell death. More information about this importance of free radicals and their role in chemistry, biochemistry and medicine can be found in these articles. So let us now study the formation of free radicals. Free radicals are formed mostly by bond dissociation and bond dissociation is of two types that we have studied earlier, homolytic and heterolytic. So it is the homolytic bond dissociation process that leads to the formation of free radicals. And free radicals can also be formed by reactions of free radicals with other compounds. So in this first example, which is homolytic bond dissociation, bond between atoms A and B is breaking to give us two radicals. But in the other example, a radical is reacting with a normal molecule to give us another radical. So X radical character of X is getting transferred to A. And bond dissociation obviously requires energy that we are popularly calling bond dissociation energy. Bond dissociation energy is defined as the energy required to break a chemical bond, mostly sigma, in homolytic or heterolytic. So these are some of the typical bond dissociation energy values that you will find for diatomic molecules. For chlorine it is 58, for bromine it is 46 kilocalories per mole. Iodine is much weaker, and one of the strongest bond is the hydrogen bond, which requires 104 kilocalories, and there are few other examples. The most strongest of them is the nitrogen bond. Therefore N2 nitrogen gas is very stable and doesn't react easily. And these are some of the typical bond dissociation energies for small organic compounds, and you will find that most of these values are above 95 kilocalories per mole. And of note is the fact that the difference between single, double and triple bonds is not always what you expect. So we can discuss these trends in these bond dissociation energies in detail later on. Now let us try and understand how these free radicals are formed in some detail. We have seen that mostly the bond dissociation energy for many compounds is more than 95 kilocalories per mole. Therefore forming free radicals is not easy, and generally high temperatures will be required if you want to form alkyl radicals just by heating, and therefore most of the compounds will either boil at this temperature or will degrade. Therefore just heating compounds at high temperatures is not the best way to generate free radicals in a controlled manner. Therefore to generate free radicals in controlled fashion, we need radical initiator. These are mostly peroxy or azo compounds which contain weak oxygen-oxygen or nitrogen-nitrogen bonds. And typically these bond dissociation energies are around 40 kilocalories per mole. And thus these radicals will form at a lower temperature of anywhere between 60 to 130 degrees Celsius. So these are the thermal methods of radical generation, in which tertiary butyl peroxide is heated at 100 to 130 degrees. Oxygen-oxygen bonds break homolytically to give us the tertiary butyl peroxy radical. Similarly, other peroxides like dibenzoyl peroxides are, when they are heated, the oxygen-oxygen bonds break and we get the oxybenzoyl radical. Similarly, other nitrogen-containing compounds like the azo-bis-isobutyronitride, which is this compound which contains a nitrogen-nitrogen bond. When this is heated between 60 to 100 degrees Celsius, the nitrogen-nitrogen bond break to give us alkyl radicals. The importance of this compound is that it gives us access to alkyl radicals easily. But there are other methods like photolysis, that energy of light we can use to form free radicals. And this chlorine, when treated with light, will give us chloride radical. Similarly, acetone, if it is exposed to ultraviolet radiation, it will form acetyl and methyl radicals respectively. These initially formed radicals are then used for performing other reactions like abstracting a proton from other molecules. So reactions of free radicals are of few types, and but all these reactions have three common components in them. They are initiation, propagation, and termination. So first we will take a look at the initiation reaction. Free radicals are very reactive and usually oxidize other compounds. So these can be initiated by, as we have seen earlier, that tertiary butyl peroxy radical can be generated from the corresponding peroxide compound. And these free radicals, once they are generated, they are in need of electrons. So they take electrons from other and in effect oxidize other molecules. This tertiary butyl peroxy radical, if it comes in contact with the hydrogen bromide, it will abstract the proton to form the tertiary butanol and free bromine radical. So these initially formed initiator will generate radicals. These will react with other molecules to generate new types of radicals. So these new radicals are relatively less reactive than the earlier ones, and thus they can stay along in the reaction mixture for some time to react to perform other reactions. So these step 1 and 2 together, they are known as initiation steps in the free radical reactions. Once these free radicals are generated, these can further react with other compounds which are electron deficient or electron rich, and can form can react with the electron rich centers and to give us other radicals. This, as you will see, lead to the formation of carbon-centered radical, which will further react with another molecule of hydrogen bromide to give us the bromine radical back. So this third step can start again with another molecule of alkene. So we here see that the bromine first reacts with alkene, gives us an alkyl radical. Alkyl radical takes a proton from the HBr and gives back the bromine radical. This further reacts with alkynes and chain propagates. Therefore, these 3 and 4 are known as propagation steps. And the steps 3 and 4 will keep continuing sequentially to form more products till the time termination steps happen. So one of the molecules of the initiator usually reacts with thousands of molecules and propagate the reaction. But ultimately, these radicals will be neutralized or killed in other reactions. Such reactions are known as termination reactions, and they usually comprise of two radicals reacting with each other to give neutral molecules which cannot react further. So, for example, two bromine radicals, if they come in contact with each other, they will form the bromine molecule. Similarly, if two alkyl radicals come too close to each other, they will form the carbon-carbon bond and give us that alkane type framework. On the other hand, the bromine and the alkyl radical will react with each other to give us that carbon-bromine bond. So all these steps will lead it to termination because they don't generate new free radicals, and the reactions will stop because of termination reaction. So let us in the next lecture see more about free radicals and their reactions. Thank you.